Hi, my name is Sydney, and for the second semester final, I'm reviewing Season 11, and this is my review video. The first part to Season 11 is called Simple Harmonic Motion. This is a motion that repeats itself over time. Some examples of this are a pendulum, trapeze artist, or a spring block. All of these repeat motion over time. So there are 2 points in the path that undergoes simple harmonic motion. The first is called the equilibrium position, which is the position where the object starts. For the pendulum example, this would be the hanging point, and for the spring block, it is where the spring is fully unstretched. The Ke value and velocity are at a maximum for this, and the Pe is at a minimum. The second point would be the maximum and minimum position. At this, the Pe with force and acceleration are at a maximum, and the Ke and velocity are at a minimum. The next part of simple harmonic motion is the restoring force, which is the acceleration or force acting on an object. For example, for a pendulum, the force would be gravity. And the next important thing in simple harmonic motion, which will actually be the last, is that if you ever see the letter K, that is qualified as spring constant, and that is for the spring box. So the second part of Season 11 is called Hooke's Law, and it's represented by the equation below. This equation is the elastic force of the spring is equal to the negative spring constant multiplied by the displacement. And a few key things you should know about Hooke's law is that in simple harmonic motion, the restoring force is proportional to displacement, which is why it's in this equation. And the further the string is stretched in the spring box, the greater the restoring force. And then lastly, that the force will act in the opposite direction of motion. So here's my practice problem, and it's if a mass of 0.55 kilograms attached to a vertical spring stretches the spring 2 centimeters from its original equilibrium position, what is the spring constant? So right now, what I can tell you is that we are looking to find the spring constant in this equation. And to start off this equation, I'm going to write a knowns table and create a free body diagram. So in my knowns table, I have that the mass is equal to 0.55 kilograms and the displacement is 2 centimeters, but we don't want to work with centimeters, so I converted it to meters, which is 0.02 meters. And the next step is creating a free body diagram. So for my free body diagram, I know that I have the force of gravity going down, and that I also have the force of the spring, which is repelling it back up. So there are only 2 forces acting upon it, and both of these forces are actually equal to it. Now with this free body diagram, what I can do is find my spring constant through it. So my equation is going to be 0.55 kilograms multiplied by the force of gravity, which is 9.8, and this equals 5.39 meters per second squared. My next step is going to be to write my equation out. And if you don't remember, it is spring force equals negative spring constant multiplied by the displacement. So now that we have our equation, we're going to plug some numbers in. So to start off, I'm going to have 5.39 is equal to negative k, since we're trying to find the spring constant, multiplied by 0.02 meters. And instantly I'm actually going to make the 5.39 meters per second negative because the spring is going down and there's a negative force on it. By doing this, I cancel out my negatives. The next step in finding k is dividing both sides by 0.02. While doing that, we solve for k and we get 270 newtons per meter. This means that it stretches the spring 1 meter with 270 newtons on it. So the third part of season 11 is called Measuring Simple Harmonic Motion. And right here I have just two charts. And what you can see here in maximum displacement is that the PE is at a maximum and that the KE is at a minimum. And if we look at the minimum displacement, that is the same thing. But if we look at the equilibrium, the PE is at a minimum and the KE is at a maximum. So they actually are complete opposites of each other. And then this chart right here is what I'm about to go over. And if later in the video you don't understand, you can always look back here and hopefully it'll make more sense. So right up here, this is an example of a roller coaster ride that you've possibly ridden at Six Flags or a different amusement park. But this is a pendulum. And what I was showing you on the previous page was a chart that reviewed amplitude, period, and frequency. And the amplitude was the maximum displacement from the equilibrium position. And this is in meters or any form of distance, so centimeters. And then the period is the time it takes an object to do one complete cycle, and this is measured in seconds. And period is actually symbolized by the letter T. Really makes no sense why it is, but if you see the letter T, it means period. And then finally, frequency is the number of cycles per second, which is in hertz, which honestly means cycles per second. So if that helps you remember frequency, I would use that. Frequency is symbolized by the letter F. So the equation to find frequency is right down here. It is F equals 1 over T, so frequency equals 1 over the period. And a thing to note is that the period of a pendulum is individual of the mass. Another fact is that in a spring box, the length of the string actually corresponds to period. So as the string shortens, so does the period, and when it lengthens, the period rises and increases. Now, if we're comparing Earth to gravity on the moon, which is actually 1/6 of gravity on Earth, the period becomes slower because there's less force on the pendulum. And then if we're comparing to Jupiter, the period becomes faster. And if it's in an area with zero gravity, there's an infinite period and the pendulum doesn't move at all. The final part of measuring simple harmonic motion is the period of simple pendulum in simple harmonic motion equation, which is right here. And this is T equals 2 pi square root L over AG, which is the period equals 2 pi multiplied by the square root of length divided by free fall acceleration. So the fourth part of season 11 is mass spring systems. So a few important things that I'm going to review here is the first one is when mass is decreasing, the period is as well decreasing. Also, the spring has more restoring force when K, or the spring constant, is higher. And also, M is directly proportional while K is indirectly proportional. So I'm actually going to do a practice problem. So the problem reads, the body of a 1,275 kilogram car is supported on a frame by 4 springs. 2 people riding in the car have a combined mass of 153 kilograms. When driven over a pothole in the road, the frame vibrates with a period of 0.840 seconds. For the first few seconds, the vibration approximates simple harmonic motion. Find the spring constant of a single spring. Immediately, I know that in a car there are 4 wheels, or 4 springs. So right now, I'm going to remember that in the end of the problem, I'm going to have to divide by 4 to find the individual spring constant for one of the springs, not the 4. So right now I'm going to create a table of knowns, and then as well I'm going to write down the equation so that we can plug in information. Right now I know that the mass of the car is 1,275 kilograms. The mass of the people is 153 kilograms. And then the time is 0.840 seconds. So what I was saying up here is that we are going to have to divide by 4. So right now I'm going to do the mass total, which is 1,428 kilograms, and divide that by 4. And then from there I get 357 kilograms. And now that I have all the appropriate information, I'm going to start plugging things into my equation. And if you don't remember the equation, it is T equals 2 pi square root m over k. And after plugging in my information, I get 0.84 equals 2 pi multiplied by square root of 357 over k. Remember, k is what we're finding. We are finding the individual spring constant. Now, to solve this equation, what I'm going to do is I'm going to start off by dividing both sides by 2 pi. And then from there, I'm going to square both sides. And then I'm going to cross multiply. And once I do that, I get k is equal to 2 times 10 to the 4th power newtons per meter. And that's your answer for the spring constant of a single spring in this car. The 5th part of Season 11 are properties of waves, and the key part of this is the medium, which is materials that waves travel through, and ripples and waves are the disturbance in mediums. 2 types of waves that there are periodic waves, which are continuous pulses through the wave, and pulse waves, which are a wave that you can create by connecting a string to a wall and moving the string up and down, and these are single disturbances through a medium. Here are pictures of a transverse wave and a longitudinal wave, and a transverse wave is a medium that moves perpendicular to the wave, and a longitudinal is a medium that moves parallel to the wave. Part of waves is the rarefaction and compression. Rarefaction is low density and compression is high density. And then right here you can see my really bad drawing of a wave, but up top here this is called a crest, and down here this is called a trough. And an important part of waves is that the wavelength is the full length of a wave in meters. The final part of this section of Season 11 is the equation for speed of a wave, which is speed of wave is equal to frequency multiplied by the wavelength. And the 6th part of Season 11 is called wave interactions, and right here you can see another poor drawing of mine. And I drew this because 2 waves can occupy the same spot at the same time. This is called superposition. And the next part is called constructive interference. This is when 2 waves overlap, superposition, and they actually add together to create a third wave. So this wave right here is the sum of the pink and the blue wave added together. And then there's destructive interference, which is where the 2 waves overlap or superposition, and they actually subtract the sums. So if you subtract the sum of the pink wave from the blue wave, you end up with a green wave like this. And now we're getting to fixed and free boundaries. Now, a fixed boundary is a reflected pulse that stays on the same side as the incident pulse. And a reflected pulse is the returning wave, and the incident pulse is the incoming wave. The free boundary is where the top reflects the down on the bottom, and it's actually just the opposite of a fixed boundary. And if you didn't understand what I just said, here is a visual. The left is the boundary free, and the right is the boundary fixed. And we've come to the final part of Season 11. This is the standing wave. A standing wave is a wave pattern that develops when 2 waves of same frequencies or amplitudes and wavelengths travel in opposite direction and interference. In the last part of this video, I'm going to discuss nodes and antinodes. Nodes are points where the slinky or string doesn't move. This is by destructive interference. It is these right here. All of these are nodes, lots and lots of nodes. And then up top are the antinodes. Antinodes are where the max amplitude is on the wavelength chart. And this concludes my video. I hope you got a nice review of Season 11, and best of luck on your finals.